अस्सलाम वालेकुम सर।
वालेकुम अस्सलाम।
वालेकुम सर।
वालेकुम अस्सलाम। केड़ा हाल है? ठीक है?
अल्हम्दुलिल्लाह साईं, तव्हां ॿुधायो त वैसे ही आहे?
हाँ अल्लाह साईं एहसान बिल्कुल ठीक।
ठीक।
गफूर सुभाणे जी मीटिंग में छा एजेंडा आहे जेका 2 खां 4 वारी?
जी जी, त सुभाणे जेका मीटिंग आहे हुन में जेको बेस लाइन वारो जेको आर्टिकल हले थो उनजे बारे में ऐं ॿियो जेको मां मल्टीलिंगुअल ते कमु पियो कयां उनजो राइटअप ते कमु थो कयां उनजे बारे में थोरो प्रोग्रेस हूंदी।
प्रोग्रेस आहे माना सुभाणे कुछ हूंदो न?
जी जी, असल में डेली बेसिस ते मां कॉन्टेक्ट हूंदो आहे डॉक्टर अली सां, त पोइ अपडेट कंदो वेंदो आहे डॉक्यूमेंट, उहो रिव्यू कंदो वेंदो आहे।
ठीक है, माना इहो तव्हां ॻाल्हि करियो पिया जेको इहो राइटअप जे हवाले सां न?
जी जी, मल्टीलिंगुअल वारो।
ओके, मल्टीलिंगुअल वारो उनजे राइटअप जे हवाले सां। ऐं
जी जी,
उहो डेटा सेट जेको DIB वारो पेपर हो रीसबमिट थी वियो?
हाँ सर, उहो रीसबमिट थी वियो। हुन में जेको इशू हो रिज़ॉल्व थी वियो, जेको हुन वारो हुयो उहो रीसबमिट थी वियो आहे। ऐं बेस लाइन वारो जेको डेटा सेट हो उहो मां फाइनलाइज़ करे छॾियो, सारंग खे शेयर करे छॾियो। सारंग हुन ते एक्सपेरिमेंट परफॉर्म करे पियो। ऐं जेको मुंहिंजो थीसिस वारो जेको डेटा सेट आहे उहो बि तक़रीबन हाणे फाइनलाइज़ थियण वारो आहे। उन ते तक़रीबन मां कमु करे चुको आहियां, हाणे सिर्फ़ु एक्सपेरिमेंट उन ते परफॉर्म करणु आहे।
ठीक है, ठीक है, ठीक है, सही सही। सैफ तव्हां ॿुधायो कीअं आहियो?
सर ख़ैर लॻो पिया, अल्हम्दुलिल्लाह। सर तव्हांजो हाल अहवाल?
शुक्र अल्लाह साईं, मालिक आहे करम। माना अॼु ख़ालिद त भाई तो नवाब शाह हलियो वियो आहे।
हाँ सर, मां भी घर आयल आहियां। बस मां भी हिते मिड़ई जॻह का ॻोल्ही आहे क्लास अटेंड करण लाइ।
घर माना ॾी लड़काणा न?
घोट नवंदेरे। हाँ नवंदेरे।
अच्छा अच्छा अच्छा, सही
हाँ
सही सही। आऊं हिते ही आहियां, आऊं ही सॼो वीक हिते ही आहियां। ऐं
अच्छा सही है। मां मंडे ते अची वेंदुमि सर, इंशाल्लाह पोइ वरी मिलंदासीं।
माना एनी टाइम। ही त ॾींहं एॾा आइडियल आहिनि, माना सॼो ॾींहुं बिल्कुलु केर बि डिस्टर्ब करण वारो कोन्हे, कमु ई आहे। ऐं इलाही सारा पेपर आहिनि जंहिंजा कुझु जा रिव्यूज़ आयल आहिनि, कुझु जा हींअर इहो सारंग सां गॾु जेको कमु कयोसीं थीसिस वारो, उन जो रिसेंटली फर्स्ट रिव्यू आयो आहे। उहो वारो जनरल आहे पैटर्न रिकग्निशन एंड आर्टिफिशियल इंटेलिजेंस। उहो माना ॾाढो एक्सीलेंट क़िस्म जो जर्नल आहे ऐं उन जा रिव्यूज़ आया आहिनि, उन ते कमु करिणो आहे। ऐं ॿियो वरी ही जेके असांजा हलनि पिया मीटिंग्स एवरी सैटरडे, इन जा इलाही सारो कमु पुठियां रहिजी वियो आहे मुंहिंजे ॿिनि हफ़्तनि जे एब्सेंट जे करे। त हीअ त आइडियल टाइम आहे ऐं मंडे एनी टाइम।
सही आहे सर, सही आहे।
गफूर, तव्हां बि जेको तव्हांजे MS थीसिस जे हवाले सां तव्हांखे ख़बर आहे न तव्हांजी डेडलाइन कहिड़ी आहे?
सर 30 मार्च ताईं जेको सर थीसिस जेको आहे न रिपोर्ट जमा करणी आहे।
हाँ न, त तव्हां पोइ गॾोगॾु थीसिस लिखंदा वञो। माना
जी जी सर, सर राइटअप ते मां MS वर्ड ते कमु कंदो थो हलां। सिर्फ़ु हाणे लेटेक्स ते डॉक्यूमेंट मिलियो आहे, फाइल जेको आहे मिलियो आहे, हाणे सिर्फ़ु मां हुन ते अपडेट कंदो वेंदोमांसि। मतिलबु राइटअप ते कमु कंदो थो हलां हुन सां गॾु।
ठीक है। असल में इम्पोर्टेंट इहो त आऊं चाहियां थो त तव्हां न इहा डेडलाइन मिस न करियो। पॉइंट 1 पॉइंट 2 हीअ त जंहिंमहिल पाण 30th ऑफ मार्च के पहुचूं त बाय दैट टाइम तव्हांजा 2 इम्पैक्ट फैक्टर हुअणु घुरिजनि। माना हिकिड़ो इम्पैक्ट फैक्टर तव्हांजो इहो DIB वारो थी वेंदो ऐं ॿियो इम्पैक्ट फैक्टर इहो तव्हांजो जेको बेस लाइन वारो इहो थी वञणु घुरिजे न। त इहे जेकॾहिं 2 पेपर तव्हांजा एक्सेप्ट थियल हूंदा त तव्हांजो ॾाढो सम्झो त हिकिड़ो बहितरीनु इम्प्रेशन हूंदो त तव्हां MSc थीसिस मां 2 इम्पैक्ट फैक्टर पेपर कढिया आहिनि न। ऐं इवन इहो असां बि कोन कयो। असां जॾहिं AIT में MS कईसीं त हिकु पेपर बि कोन कढी सघियासीं। हालांकि असांखे ॾाढो सुपरवाइज़र इनकरेज कयो हो ऐं हुन एक्सीलेंट मूंखे ॾिनो हो थीसिस में, इन शर्त ते तव्हां पेपर कढंदुसि, पर डिग्री जीअं मिली त ज़ाहिर आहे ऐं पाकिस्तान में थाईलैंड में पोइ असां हुनखे माना कॾहिं लिफ्ट ई कोन कराईंदी न। त हा, ईअं न थिए। तव्हां जेको सो GIB वारो आउं एक्सपेक्ट करियां पियो त विदिन कपल ऑफ वीक्स पाण डिसीजन हूंदो। ऐं बाक़ी ॿियो आहे बेस लाइन वारो, उहो थोरो माना जनरल बि ॾाढो ज़बरदस्त आहे। जेका ट्रांजेक्शन आहे हिन वारी लो रिसोर्स लैंग्वेजिस वारी, इन में पाण खे सबमिट करिणो आहे ऐं ॾाढो क्वालिटी राइटअप इंशाल्लाह। ऐं पोइ हाणे सुभाणे जी मीटिंग खां पोइ वरी कंट्रीब्यूट करणु शुरू कंदो ही सम्झो था 6 ॾींहं कुझु बि कंट्रीब्यूट कोन कयो आहे कंहिं बि शइ में त हाणे वरी इंशाल्लाह आफ्टर टुमारोज़ मीटिंग आई विल बी बैक इन फुल स्विंग
जी सर ऐं सर टियों आर्टिकल बि आहे जेको मल्टीलिंगुअल वारो आहे जेके जंहिं ते मां ट्रांसलेशन कई उहो बि तक़रीबन सुठो कमु कयो मां उन ते बि राइटअप उन ते राइटअप ई हले पियो उहो बि तक़रीबन हाणे IEEE एक्सेस जे उन ते फॉर्मेट ते राइटअप कयूं पिया मतलब इंशाल्लाह उन ते कमु सुठो थी वेंदो 3 खां थी वेंदो इंशाल्लाह
वो मूंसां शेयर थियल आहे न
सर वो तव्हां सां ओवरलिप जो फाइल शेयर थियल हूंदो मुंहिंजे ख्याल में डॉक्टर अली चयो
ठीक है
राइटअप मां पे कयांसि न त मां शेयर करे वठंदुमि तव्हां सां
ठीक है न इहो मूंखे यादि आहे तव्हां
हुन में रिलेटेड सेक्शन जेको कम बि कंप्लीट करे चुको आहियां ऐं जेको ट्रांसलेशन एंड मेथोलॉजी उहा बि तक़रीबन कंप्लीट थी चुकी आहे हाणे बस इंट्रोडक्शन थींदो ऐं जेके रिजल्ट वग़ैरह डिस्कस थींदा
जबरदस्त यार जबरदस्त एक्सीलेंट क़िस्म जी प्रोग्रेस आहे ऐं माना जेकॾहिं इन ई पेज ते असीं रहियासीं त तव्हांजी थीसिस त बिल्कुलु बि टाइमली कंप्लीट थियणु घुरिजे ऐं तव्हां त इंशाल्लाह काइंड ऑफ रिकॉर्ड टाइम में MS कंदो तव्हांजी एडमिशन कॾहिं थी आहे
सर fall 2019 मतलब 1.5 साल अञा थियो आहे मूंखे
है ना fall 2019 ऐं विच में कोविड वेॾा वॾा पर उन बावजूदि तव्हां प्रोपोज़ल बि थी वियो आहे ऐं जेकर तव्हांजो 30 मार्च तव्हां जेकर थीसिस सबमिट करियो था माना 30 मार्च में अञा 3 महीना आहिनि न ऐं तव्हां ऑलरेडी लिखो पिया तव्हां ऑलरेडी पेपर लिखो पिया तव्हां टेक्स्ट हूंदो तव्हांखे कुझु न आहे करिणो रुॻो हुनखे हिन फॉर्मेट में खणी अचिणो आहे ऐं 30 मार्च तमामु घणो टाइम आहे न माना 30 मार्च में अञा बि सम्झो त lot of time is still there
मुंहिंजो टारगेट फेब्रुअरी आहे
हा न तव्हां मूंखे ज़ाहिर तव्हां मूंखे 15 फेब या अराउंड 20 फेब मूंखे ॾींदो छाकाणि त मूं वटि तव्हांजे बैटरी साइकिल थींदा न माना हिकिड़ो तव्हां सबमिट कंदो रिव्यू कंदो वरी सबमिट कंदो वरी रिव्यू कंदो त मुश्तबा खे तॾहिं सबमिट थी जॾहिं ज़ाहिर पाण ॿई एग्री कंदासीं न त 30 मार्च त सम्झो त आहे डिपार्टमेंटल डेडलाइन न पर मूं वटि तुंहिंजी डेडलाइन माना राइटअप जी आहे 15 फेब त 15 फेब ते तूं हुनखे कंप्लीट कर त पोइ आउं तोखे विदिन 5-10 डेज़ आउं फीडबैक ॾियां ऐं by March 30 we should be submitting to department and department bhi हींअर fully committed आहे त असांखे इहे जेके रेड टेप्स आहिनि उनखे एलिमिनेट करिणो आहे असां वेरी क्विकली एक्सटर्नल बि इलाही सारा आहिनि असां आउं त सोचियां पियो डॉक्टर अली खे रिक्वेस्ट कंदासीं त एक्सटर्नल थिए या इन्हनि खे त अहिड़े क़िस्म जा या वरी लम्स वारो हिकिड़ो आहे जंहिं ॾांहुं असां सारंगी थीसिस मोकिली उहो ज़बरदस्त आहे नस्ट वारो हिकिड़ो आहे उनखे बि मोकिलीसीं all these are good guys and they very quickly give feedback एतिरो टाइम किल कोन थींदो त कोशिशि पंहिंजी आहे त तव्हां स्प्रिंग 2020 में न ग्रेजुएट थी वञो ताकी असां जेको कमिट करियो न 2 सालनि में MS विथ थीसिस त उहा थी वञणु घुरिजे इरफान बि अगरि ॿुधे पियो
सर मूंखे बि 2 इयर्स में करणी आहे सर
यार इहो थोरो वाला हलो पिया पुठिते छाकाणि मूंखां
एक्चुअली सर अब्दुल गफूर खे इहो एडवांटेज आहे त हिन कोर्सेस घटि कया न असां मां कोर्सेस कंप्लीट आहिनि मुंहिंजा न त मुंहिंजा नेक्स्ट 6 मंथ जस्ट थीसिस ई आहे त
सही न तव्हां आउं त चवां थो त ही आइडियल टाइम आहे हींअर तव्हां
बिल्कुलु
जॾहिं बि चाहियो अची मूंखां मिलो ऑफिस में वेठो आहियां ऐं पाण हिन कम खे अॻियां वधायूं ऐं तव्हां लास्ट सैटरडे जी मीटिंग अटेंड कान कई हुई मूं मालूम कयो
सर एक्चुअली हाज़िर मां वियोसि ऑफिस उते सैटरडे ते असांजी मीटिंग फैकल्टी हिन जी इंडस्ट्रियल लियन कमेटी जी हुनजो सर मां आहियां सेक्रेटरी इनजे करे सर मां अची न सघियसि ऐं उते मुंहिंजी मोबाइल फोन बि सही चार्ज न हुई त मूं रिप्लाई बि न करे सघियसि न त ग्रुप में इंफॉर्म कयां सॉरी सर हुनजे लाइ एक्चुअली मीटिंग में हुयो
अपडेट वरती मूंखे ख़बर पई त सभु आया हुआ ऐं सवाइ इरफान जे
हा सर मां ॾाढो मिस कयो सर हुनखे
हलो ठीकु आहे
इंशाल्लाह सुभाणे ज़रूर सर
हा सुभाणे अटेंड करियो ऐं कुझु प्रोग्रेस आहे
जी जी सर जी
चलो ठीक है ये रिपोर्ट डिस्कस करा दी it's already 4 p.m. so we are formally starting we are yet to be joined by Abdullah Hasib Nimra is there Nimra is there no Nimra Nimra is here and okay, so we can start. Others can join in the process. So let me reconnect with what we covered previously. I hope you can see my screen.
Yes, sir.
Okay.
Yes, sir.
Okay. So in the last class we covered the concept of this neural machine translation, a beautiful concept. We have discussed all these things. The role of encoder decoder. I mean, in past they were RNNs, could have been LSTM or any other thing. So these things we have covered in full detail. The neural machine translation. RNN, you know, this is RNN, huh? A simple RNN. We have got previous hidden state, current input, and then we have got that beautiful formula of activation between previous state and current input. You already know the mathematics behind that. So all these things we covered in the previous class. We now should be clear with the concept of attention model and with the concept of transformer. Now remember, BERT is nothing, just a different connectivity of the concept of attention. So I don't think I need to cover BERT. You just need to see how different connections are made between encoder and decoder for BERT. Otherwise, BERT is exactly same as the transformer model. So I'm not going in a lot of detail of BERT. Neural machine translation, we saw the translation between German and English, and I gave assignment of Urdu to English. Have you people done that? Anyone willing to share that? Vishal, I think you were doing on your local language. Did you complete that? Hello, Vishal, can you hear me? Vishal, we cannot hear you. Though you are unmute. Saif, have you implemented Urdu to English? Hello. Abdul Ghafoor?
Yes, sir.
Have you implemented Urdu to English?
Sir, मां कौन कही खोलियो हुयो पर उनखां उते ही रही जियो मूंखां.
Irfan?
Sir, to be very honest, try न कयो
No,
actually
sir.
असां हुयासीं बिज़ी हुन कम में ऐं प्लस में यादि बि सर न रहियो न उन
Saif?
ॾींहुं यादि आहे तव्हांजो मैसेज
Saif?
सर कंदुसि पर
Sir,
ज़रूर.
no one completed, sir. Inshallah, we will do it soon.
Vishal, why not? Vishal?
Sorry, sir.
Vishal? Vishal, your mic is unmuted. I don't know why we cannot hear you.
Vishal, connect your mic. Your mic is not connected.
I think Vishal was in discussion with me on WhatsApp, discussing that he will be doing it in Tamil. So I said, okay. So I'm hopeful that he might have done something. I mean, you need to understand that concept is same. It is exactly same code. You just need to change a couple of parameters and use, different data set. And data set I've already shared. That is also available on LMS. So you need to do nothing. Just kind of walk in the park assignment. That is the reason why I did not make it graded assignment. It was ungraded, and probably that is the reason why you did not take it seriously. It was ungraded assignment. I said you will have to download this English to Urdu data set. This one we have already done, and I think I also shared the code. So should have been done. Anyway, I'm hopeful that you will do it in coming few days, because
Inshallah, by Sunday, inshallah.
okay.
I
So
preach.
I'm going to create assignment. I'll make it graded, because ungraded you will take it seriously. So I'm going to make it graded assignment so that you can take it seriously. Otherwise, no grades, no submission. 8. It's assignment Urdu to English NMT. Urdu to English neural machine translation. So this is an assignment that you need to submit. You already know what is that. I'm not writing any text here, but you need to submit it by Sunday. Sunday means Jan 3rd, and by 23:59 you need to
Sir,
submit.
make it Monday or Tuesday.
Monday or Tuesday. Okay.
Yeah, sahi hai, sir.
Okay. Okay. So it will be a file submission of any type, but you will submit Python, eh? You know what? You know this, eh?
Yeah, sir. Yeah, sir.
Okay. Submission setting, it has to be group submission or grade 100 points, eh? So I hope you will submit it. So please do this. I was very much excited. I actually want to see it. I want to see it. How many of you have understood, you know, this German to English to German? So let's see if you can do this.
Inshallah.
Okay, okay. So all these things are clear. The concept of transformer we discussed in a lot of detail. The video is still there if you want to see it again. We also understood the mathematics behind attention and transformer. All these things are well covered, right? Attention, you know, these three vectors, query, value, and key. These things we covered in a lot of detail. All these states we covered in the previous class. So transformer is complete. If you only see BERT is using, you know, transformer architecture, BERT architecture. So you will see that it is almost same, except couple of connections are different. I mean, if you see here, BERT architecture, सर अस्सलाम वालेकुम. हाँ सर क्लास पे उठा. Okay, so if you see BERT architecture, it is, this is BERT, this is OpenAI GPT. You will see that both GPT and BERT, they are using transformer. They are using this attention mechanism. Is internet slow or what? This is OpenAI GPT. Each of these are actually, you know, transformer models. So you already know transformer. So it should not be, you can see both of them. I mean, all of these, this is BERT and this is OpenAI GPT and this is Elmo, and all three are using transformer, the attention mechanism. The only difference is the connection is different. You can see BERT has more connection than OpenAI GPT. This is probably more complicated than OpenAI GPT, right? I mean, there are just few small tricks, otherwise everything else is same. So if you understand transformer and attention, BERT and OpenAI GPT is already clear. And when you want to use BERT, you need to do nothing. You just need, the way we were using glove, same way we can use BERT. I mean, pre-trained, you know, word embedding. You can see I have used it with sentiment 140. So once if you are clear with the theory of transformer, BERT is automatically clear. And then when you want to use its implementation, you can see I'm using it with sentiment 140, and you know what is sentiment 140. We have been using this very extensively. So you need to download BERT, rather install BERT. I mean, here pip install transformers, you will install transformers, and then once if it is installed, you will import BERT tokenizer. You can see here, this is Twitter, you know, auto model that from pre-trained BERT base, right? So this actually loads pre-trained BERT model. This is unlike GitHub. We are using it as a pre-trained word embedding, but the difference is this time you will not be, having any vector file, but you will actually import this from auto model library. So from pre-trained BERT base and case, you will load it, then BERT tokenizer, and then you can use it the way we have been doing in past. So I'm going to share this document with you. This will, if you want to see how BERT is being shared, you can see this one. I'm sharing it with Irfan. Irfan, please share it with others. Irfan?
Sure, sir.
Is this your email?
Yes, sir.
Irfan.
Irfan.Memon.
.memon, eh?
Yes, sir.
Okay. So this code actually gives you an understanding how BERT should be used with the LSTM. Okay, now we shift our focus to two remaining topics. One we will cover today and one we will cover next Friday. Next Friday will be our last class because I have missed 2 classes. So I'm going to compensate both of these. One will do today and other will do on January 8th. So today we'll cover autoencoder, and next week we will cover again, generative adversarial network. And next week I will also give you a couple of running examples of GPT-2 and GPT-3. So next week will be our last class, and this week we are going to cover autoencoder. Autoencoder is yet another very exciting topic. I mean, everything in deep learning is exciting, but this autoencoder and GAN, these are two yet two more very exciting topics. What we will be covering today, we'll see autoencoder application, where they are used, the principles of autoencoder, its implementation, and then 2 application of autoencoder in denoising and encolorization. Believe me, I mean, those who still have not selected thesis topic, for them this can be very fascinating. I mean, these two, autoencoder as well as GAN. So autoencoder will cover today and GAN will cover next week. But these all are very exciting new addition in the area of deep learning. I mean, these things which otherwise probably were not being covered in machine learning, but because of the advent of deep learning, now we are able to do these things as well. So autoencoder, they are used for denoising. I mean, just imagine if you have got some papers from 19th century and you want to denoise them, you scan them and you want to remove noise from those documents. I mean, those very old papers which now are partially damaged, and if you want to recover a text from those, if you want to remove noise from those images, autoencoders can be used. So one of the application of autoencoder is to eliminate noise from the image. It's not only that you eliminate noise from the old document, but even if you have taken an image today and if there is a lot of lighting, so you can use autoencoder to improve those bright spots. You can also do colorization. Just a minute, I mean, let's wait for the azan. Colorization is another application of autoencoder. I mean, you've got grayscale images and you want to colorize them. I mean, your deep neural network will automatically learn what color I should apply on the face, what color I should apply on the green field. I mean, you give it a grayscale image it would have already learned how a sky looks like, how a tree looks like, how a human looks like, how a computer looks like. I mean, you just train it properly. You show him that what colors should be applied on different items in real world. Your model should be able to convert a grayscale into a color image if you just provide a proper training. So colorization is another application of autoencoder. Then object detection, tracking, segmentation, all these, I mean, even otherwise without the support of autoencoder, we'll be able to do it. But these type of things can also be done with the autoencoder. We will not be covering object detection, tracking, and segmentation, but we'll be covering denoising and colorization, how to do these with autoencoder in today's class. So here is simple principle. I mean, what autoencoders actually are. I mean, see the beautiful concept, see the beautiful idea. Give it an input image. We will have an encoder. This encoder can be fully connected neural network. It can be CNN. It can be RNN. It can be LSTM. But RNN and LSTM probably are better suited towards encoder, which are there for text. But if you are playing with the images, then you will probably use either fully connected dense neural network or you will use CNN. Believe me, I have not seen a lot of literature which uses autoencoder for playing with text. Yes, we have seen playing with the image when you are using autoencoder, but I have not seen a lot of literature where autoencoder is being employed in text mining. That is one untapped area. I mean, you can brainstorm, you can think how autoencoder can be exploited in text mining. Maybe for text generation, I'm not sure, but the thing is, you know, autoencoders are pretty extensively used in image mining with CNN, with fully connected, but I have not seen much use of autoencoder with RNN and LSTM, but you can explore it. So the idea is, you take an X, there will be an encoder, which is nothing, just function over X, some function over X. It will give you a Z. This is usually a latent vector. When I say latent vector, I mean this vector is having statistical information about X. When I say statistical information, I mean that this Z is a good representative of X. Usually, this Z is very low dimensional. I mean, if X is 256 by 256, you might have this Z as probably 7 by 7 or 16 by 16. So people say you can even use autoencoder to do compression. I mean, if you've got a lot of high dimensional images, you can represent them in low dimension, and then later on that low dimensional latent vector, which actually retains statistical information about X, it can be used to reproduce X dash, which is actually same as X, which is actually same as X. Right. So in simple terms, we say that encoder is going to change X in some way so that we have got another vector which is representing X. And because model will be kind of going through extensive training, so model will learn how to convert this latent vector back into the original X. Right. Irfan, go ahead, ask the question.
So it means, sir, we can use these encoders for text summarization because you know, it can compress an image. So in the same way, it can be used for text summarization to compress text in a more formalized and generalized.
This is something that I have not seen in literature, but I can make a lot of sense out of it. Yes, it can be used. I mean, yeah, if you give maybe 1 million documents and their summaries, then your model should be able to learn how to summarize the document. I think it's another angle. You do in literature, I have not seen it, but you are right. If we can compress image, we can also compress text. And when compressing text, that does not mean we want to save the storage. That means we want a summarized version of same text. So maybe yes, I'm not sure, but this can be an area to explore. But the whole idea of autoencoder is you have X, you do encoding. This encoding can be LST, can be CNN or fully connected. You have a low dimensional vector which is representing X, and later on decoder can recover original X from this Z. So you can use it for compression, or in some cases, say for example, see here, this one is X, this one is X dash. Now, although they look similar, but they are not same. You can see here, this is a lot different from this 7. So maybe this has eliminated a lot of noise from the input image, right? So the thing is, this one we know is 28 by 28 image, right? But we have got 16 dimensional Z, which is a vector, which is not a matrix, but a 16 dimensional vector. From this 16 dimensional vector, we apply a decoder which recovers the original image. Now believe me, this is not a copy paste. It is not that we take this image and write it on the output. No. I mean, once you have encoded, you can, forget about this X. The magic of decoder is to recover original image from the 16 dimensional Z vector, right? So you can see here, in some cases at input I might have grayscale, and here I see color image. In other application I might see here an image with a lot of noise, and here it has been denoised. Noise has been eliminated. So the whole idea of autoencoder is you must train your encoder and decoder in such a way that encoder knows what vector I should produce from each of the image, and decoder should know that what image should I produce from this low dimensional vector to a high dimensional image, right? So end of the day, this simple architecture has actually done a lot of wonders, from denoising to colorization to segmentation and to many other applications. Now let us build an autoencoder in keras. First of all, I want to show you the architecture of this model. You can see here, this is the architecture of this model. We have this encoder. In the encoder, we will have an input image, which is nothing, just an MNIST text, 28 by 28 by 1, right? Then what we are doing, we are going to have another layer of convo, which converts 28 by 28 to 14 by 14, and another layer of convo, which converts 14 by 14 to 7 by 7. And then we flatten it. When we flatten, we get these number of parameters, and these number of parameters are being converted to 16 by a fully connected dense neural network. So the encoder which we saw here, right? Input image, encoder converts to 16 dimension. You can see here input image, CNN, and it converts into 16 dimension vector. Right, so this is encoder. The decoder is, it will get 16 dimension at the input, because this is, you can see the diagram, 16 dimension at the input. So here we have 16 dimension at the input. Then we connect it with fully connected neural network, and from here we convert these parameters to 7 by 7 by 64. So it's a kind of reverse. Here the last layer is 7,764. Here in decoder, the first layer is 7,764. Then we upgrade it 7,764 to 14,1464. Then we upgrade 14,1464 to 28,28,32. So you can see in encoder and decoder, filters are same. The only sequence is different. Here we go from big to small, and in decoder we go from small to big, because in the decoder we get just one vector at the input, and we need to generate actual image. So you can see decoder is given nothing, just the vector which has been generated by the encoder. So we take this vector, we have these middle layer of CNN, and they actually recover original 28 by 28 by 1 from these 16 dimension. So you can use it for compression to save the memory. You can use it for denoising. You can use it for colorization and many other applications. Irfan, go ahead.
Sir, then how this is different from sequence to sequence modeling? Because in that we have also studied this encoder part and decoder part. So it means this can also be used for sequence to sequence text generation and translations. These encoders, autoencoders.
In a way, yes, sequence to sequence modeling. The only difference is, when we saw that sequence modeling, it was working with a sequence, whereas image is not a sequence, right? Text is sequence, your sound is sequence, your music is sequence, but image is not sequence, right? Because in image, we have got only pixels, and there in pixels, a sequence hardly matters. I mean, when you have got a sky, most of the pixels are blue, and if you change their sequence, sky will still be the sky. That is the reason why we say image is not a sequence, right? So in this case, more or less, you are right. The idea is same. The sequence to sequence is also encoder decoder, and autoencoder is also encoder decoder. But the difference is this autoencoder is not playing with sequence. Autoencoder is playing with the image, right? So it takes one image at the input and it actually generates another image at the output. Now, what is input and output? We programmer will take the decision. Okay, so you have seen these two. You have seen the encoder. You have seen the decoder. Now, the third step in keras is we put both together, right? So we will have encoder input layer. So at the input, we have got 28 by 28 by 1, right? This converts 28 by 28 by 1 into 16, and then decoder will convert 16 into 28 by 28 by 1. So in keras, we'll do these three steps: define encoder, define decoder, and then combine both of them. Right. So let's see this code. When you see the code, it will make more sense to you. By the way, this autoencoder and GAN, these are not very well written in deep learning with Python. I actually, for these two topics, I refer this book, Advanced Deep Learning with Keras. It's another fantastic book. I mean, last year I covered a lot of topics from this book, because last year I was not covering BERT, transformer, attention. So we covered many things from this book. But this year I'm only covering these two topics, autoencoders and GAN, right? Autoencoder and GAN. So all these contents which I'm covering today, they are coming from this book. And this book I have already uploaded on LMS. It's just a fantastic book. I mean, it's a kind of automatic progression from the deep learning with Python book, and then come to advanced deep learning, which actually covers all these advanced topics in keras. Apply deep learning techniques to autoencoder, GAN, variational autoencoder, deep reinforcement learning, policy gradient, and a lot more. It is also a fantastic book. But this year I will be only covering autoencoder and GAN. I mean, I wish I offer two courses of deep learning. In one semester I teach deep learning with Python, and in second semester I teach these advanced topics. But obviously, deep learning is not the only thing that you need to cover in your master's degree. There are many other courses as well. Yes, Irfan, go ahead.
Sir, are you taking any course in next semester? I mean, we were discussing that you should take a course which should combine deep learning, data science, and data mining together.
Actually, I will be teaching artificial intelligence in business in business department.
Yeah, with Dr. Wakar.
And I have
I have seen the content of that course. It's a very interesting course.
Yeah, so there are 4 sections, and I've
Yeah.
recommended them that I will teach on one condition, that Safe is joining me, because I told him that I cannot teach 4 sections. I said you need to hire one more faculty member from computer science, and when they asked the name, I said Saif or Khalid. Both of them are in computer science faculty. I said one of these two you can take on board. Only then I can teach, AI in business. But they mostly, cover the topics related to machine learning and deep learning. They will cover economics part, business part, and we people will cover the computer science side, the machine learning side actually. Anyway, that should be an exciting experience, teaching a course in business. Let's see. Okay, so now let us play with that. Let us play initially a simple autoencoder, which is doing nothing except this thing, this one, which is taking image at the input and generating same image at the output. And that image will be generated from, this low dimension vector. Let's see how to do it. So first I mount the drive, I load him in IST. You can see I'm not loading labels because I'm not interested in labels. I'm just trying to get, image at the input and image at the output, because this is not classification task. This is not classification task. So I don't need labels. So I'm not loading Y train and Y test. The reason is simple. This is not a classification task. I don't need those labels. So I'm just loading these images from MNIST. Right. The image size, it is 28 by 28 by 1. So 0 on 0 we have got number of images, which are 60,000 for taste and 10,000 for 60,000 for train and 10,000 for taste. So and the image size is 28 by 28. So I just get that image size here. Then I do X train equal to, I reshape X train all the images in image size, and the channel is 1. Right. My mobile phone has gone mad. Bixby is making assumption that I'm giving some instruction to it. Anyway, so X train and X test, I do this pre-processing, it. The input shape is image size 28 by 28 by 1. Byte size is 32, why. Filter, I mean the kernel size, which is actually in CNN it is filter, so it is 3. Right, and the latent dimension, the dimension of this vector, which I said 16, right? And in my CNN, I will have 2 layers. The first layer will have 32, 32 output, and second one is 64, right? So I say my input equal to input shape is equal to input shape, and I'm naming it encoder input. So X equal to inputs, right? And then I run a simple loop to add 2 layers in my X. Now this is functional API of keras. It is a bit different than what we have been doing so far, but ultimate idea is same. It is functional API. So all these models which we used to create as a sequential model, same we can also create with the functional API. So you can see here, this time your convo 2D is a function, and to this function I'm passing X. So I say that my X equal to create a convo 2D, filter equal to, first it will get 32 and then 64. So I add 1 layer of 32, filter size is 3, and activation is value, stride is true, padding is same, and I pass X to it. X means the input. The next time when the loop executes, we are adding second layer, which is 64, right? So next time again, filter is equal to 64, kernel size is equal to 3, activation is value, stride is true, and padding is same, right? So this for loop is actually stacking 2 convo 2Ds, right? One of 32 and one of 64, right? The other thing that I'm going to do, I say shape equal to K dot int shape. I'm doing nothing. I just get the output shape from this model, right? The reason is I just want to store, this dimension so that later I do not need to hard code it. I just want to store it in some variable because later on I will be using it. Here, my image dimension is 28 by 28 by 1. We know it, but if we do not know it, we must not do it with the hard coding. So we are actually storing, this into shape variable. The value is 28, right? So we print the shape of 1, shape of 2, and shape of 3, which is obviously 28 by 28 by 1, right? Then we flatten, why we flatten, and then we are having a dense, fully connected layer in which the output is 16, the latent dimension 16, and then we are going to give it a name. In functional API, you can assign name to all these layers, and X is our input. You know what X is representing? X is representing this whole network, because this is functional API, so you can assume this X is the model. I mean, in sequential API, we had a model, but in functional API, it is a bit different. We just, stack all the layers one upon another and store them, progressively in a variable, and in this case it is X. So initially X has inputs, then X gets the first layer of 32, then X gets second layer of 64, right? And then, I flatten X and store same thing again in X. So, again updating X. The third is I am having this dense layer, the last layer, and to this layer I'm again sending X. It means whole network is being supplied as input to this function of dense, right? So this latent is representing nothing, just complete network. So my encoder equal to, I create a model from inputs which I have defined above and the latent, the model. So we say I'm going to create a model, I name it encoder, and this is the model which we have just created, right? Two a layer of convolution and one layer of fully connected dense neural network, right? And then I'm supplying it input. Input means 28 by 28 by 1, which I have defined here, right? So this is how model is created. When you display summary, it is something like this. You can see here 28 by 28 by 1, then 14, 14, 32, 7, 7, 64, these number of parameter, and then 16. Same, this one. I have already shown you the plot of this model, right? So encoder has been created. The next step is I'm going to save this encoder. I have saved, plot of this on my drive, right? Just display it on the drive. Then the next step is we are going to build, decoder. To the decoder, input is this latent dimension, which means 16, right? Now because it is inverse, so we say X equal to dense, the shape that we stored there, 28 by 28 by 1. So we say that create a dense layer of these number of parameters, 28 by 28 by 1, which is equal to 784, and the input that we are giving it is this input, the 16, which we get from here, right? We reshape it to 28 by 28 by 1 because it is coming from a dense layer, so it is 1D. We actually convert it into 3D just by reshaping it, right? Again, we are doing it same. This time we are again using layer filter, which was 32 and 64, but this time we have to reverse. So I write here -1, right? Inverse in the reverse direction. So we will first get 64, and in the next loop we'll get 32, right? Because if you see the decoder, it is 16 to this, then this to this is the decoder model. So it is 7764. You can see 64 first, right? And then this 64 goes to 32. So that is the reason why I'm going to run this loop in reverse direction. So we create, again convolutional, 2 layers of convol 2D, And then, you know, I have output which are transpose. Filter is 1, kernel size is 3, sigmoid, that will be the decoder output, right? And here the decoder model is latent input, the outputs and the model, right? The output is actually, we are doing nothing, we just transpose this whole, you know, 2 layer into 1 by applying the sigmoid function, right? uh, we create decoder, again model, provide the input and its output, and we name it decoder. And when when you see the summary, it is same as the, you know, this decoder thing, right? And then the final thing is we create autoencoder. We give input, we say that because this is functional API, so we can call it as a function. So we are calling encoder, applying input, and whatever output we get from here, we are supplying that output to the decoder. So you know that this autoencoder, when trained properly, for each of the, you know, image, it will be generating 16 dimensional vector, and decoder for each of the 16 dimension vector, it should be able to produce the original image. Then we see the summary. The summary is actually this one. We have already discussed this summary. I'm saving it on my local drive, right? We compile it with MAC, because the loss function, if you see in encoder, the loss function is actually, you know, this one, MAC. So we see that actually here we say that from this 16 dimension vector, I want to recover original image. So when you see X initially, it will certainly will not be same as this X. So you actually do the gradient descent. So you continue improving appearance of X until your MAC approaches close to 0, right? It may not reach to absolute 0, but the thing is, you do MAC because here we are going to do comparison pixel by pixel, right? Comparison, you know, based on what is the dimension of the image. So you can see here, it runs from I equal to 1, I equal to m. In this case, it is obviously, you know, the dimension of the output image, which is 28 by 28. So we compare each pixel, right? We see the pixel on ith position in output image and ith position at the input image. We see their difference, we square them, we sum them. That is actually the mean square error. So our effort is to, you know, reduce this mean square error. So that is the reason why we are setting here the loss function as a MSE, right? Once if it is done, our whole autoencoder is set. We have coded encoder, we have coded decoder, we have put both of them together by this statement, right? By calling this model function, supplying inputs and supplying decoder, and supplying this input to the encoder and the output of that encoder to the decoder, right? We compile it, and here now see the training process. See the training process. Wow, I mean, what a beautiful idea. Extract. So we say for image I in training data set, generate image I. So we say for this image, generate for one, generate one, for one, generate one, for one, generate one. You know, 10,000 sample of one. So we are actually not 10,000, 6,000, because there are total 10 digits, 0 to 9, and there are total 60,000 images in MNIST. So we show, you know, 6,000 sample of one, and we say that when you are shown one at the input, you have to generate one at the output. When you are shown 2 at the input, you have to generate 2 at the output. But obviously, in between, you have that, you know, a low dimensional latent vector, right? So we train the model. For validation, we are supplying X test and X test, right? We say test on these images, and then, you know, when this is done, we also predict right? We are supplying, X text and do the prediction. And once the prediction is done, we are doing nothing. We are just displaying, first 8 images just to see, first 16 images just to see how, accurate these are. So the output we are saving in this file. You can see here, this is the output. I mean, no, this is for DANA. The output is in final output, example 1, final output in example 1. So on my drive, autoencoder, this one, autoencoder model, example 1, autoencoder model, example 1, autoencoder model, example 1. Right, so the output I'm saving here. So you can see here, this is the output. So first 2 row is the input and decoded are last 2 rows. I mean, you can see my logic here. What I'm doing, I'm just saying that x equal to decoded, we are predicting x text. So here numpy and concatenate, I get x text, the original 8 images, and generated 8 images, right? I get all these 16 images and display them in a grid of 4 by 4, right? And then I just use simple Python to display them. And when I display them, these first 2 rows are the original image, right? And the following 2 rows are the generated images. So you can see for 7 it has generated 7, for 2 it has generated 2, for 1 it has generated 1, for 0 it has generated 0, for 4 4, for 1 1, for 4 4, for 9 9. But you can also see the difference. I mean, this is not copy paste. You can see this 4 is a bit different. You can see these are brighter, whereas these are a bit dimmer, right? So you can see these are not exactly copy paste, but at least your autoencoder is able to learn pattern of all these numbers. So it is just like you are generating handwritten number. It is just like you are generating handwritten number. Just imagine if you, I mean, if you have got maybe 1000 pages of my writing, and if you train an autoencoder on my writing, then you can generate any passage in my writing. I mean, it will be, you can write any syntax, and you can write any paragraph which will have exact look and feel of my writing. You can generate passage written by me only if you train your autoencoder probably with 10-20,000 pages which are written, which are my handwritten. So this can be one possible application to generate handwritten text and to just kind of mimic, to simulate to some living person, right? Irfan, go ahead.
Sir, from these images, it just seems that it has just removed the extra noises. See, if you see the C original and the decoded one, it has just removed the extra noises, the pixels.
Yeah,
and
you're right.
The generated ones are more smooth than original one.
You're right. This is one aspect, but if you train it more, eventually when MSE is approaching 0, these will look more similar. Because I mean, this application, this is the first application in which we are doing nothing. We are just doing copy paste. Same, we have input and we generate same image at the output. But because we have trained only for one epoch, if you see, we are training it only for one epoch. But if you train it more, maybe this image will be more closer to this image. Both of them will be exactly same, because ultimately what we are doing, we say whatever we have at input, same thing we have at output. So our objective is to generate same image. So we say another way, we say when I give you this 7, give me same at output. Currently you can see there is some difference, but it is only because only one epoch. But if you train it more, MSE will further improve, and when MAC reaches to 0, this will be exactly copy paste of this one. This is just one application, where we are doing nothing, just copy paste. I'm saying copy paste, but if, say for example, if you have trained model, then you can forget about encoder. You just get encoded values, you just get encoded values, maybe the 16-dimensional vector. From that vector, it can generate 28 by 28 by 1 image. So you can see this is quite a lot of save in the storage capacity, a kind of compression technique. So the idea is, we have encoder, it generates a low dimensional vector, and from that low dimension vector we are able to regenerate same image that we saw at the input. Right, Nimra, go ahead, ask the question. Nimra,
sir, can you hear me?
Nimra, you have to come closer to the mic. Yeah, your voice is too low.
Hear me now?
Yeah, it's better now.
सर मैंने हैंड फ्री रिमूव कर दी, मेरी हैंड फ्री में मसला है कोई.
सही बात है. Yes, go ahead.
Sir, actually I wanted to ask, in this case where we are just copy pasting the same value in a way, so we are giving the same things, x train and x train, means input and output both are same. But in the case where we want to remove the noise, then what will be our input? Means we will be needing some noisy images and some clear images for that, for the same thing.
You're right. Very good. Very good. I'm happy that you reached there. I'm very happy. See, when you want to train an autoencoder to act a denoiser, then X test will be the noise image. X test will be the noise image here. This will be noisy image, and these will be clear images. So maybe we show to our autoencoder that these are 10,000 images which were denoised, and these are the noisy images, and these are their corresponding denoised images. So you know what it will actually learn? It will learn that which pixels are usually noisy, which pixels are usually noisy. So if, say for example, you want to have an autoencoder which removes red dot from the eye, right? So what you will do, you get 10,000 images here which have noise, which have that red dot in the eye, and here that red dot is removed. Now once if network is trained on those 10,000 images, it will automatically make sense that everything else has to be same except that red part has to be removed. Then deep learning, such is the achievement of deep learning, that you show it noisy image and their corresponding denoised images. Show them 10,000 images, it should be able to learn the pattern, and it will learn that the difference between noisy image and clean image is that red dot. So it will learn how to remove that red dot. We'll see this.
Sir, then there is one question. For example, you said in the start that we can recover the old images, means the images which are not, in their actual position. We can recover them. So how we can do that? Means I think we can't make journal model for that, because for every application the noise is different. So this is this is what is continuously this question is just in my mind. Okay, how we will do it?
Right. You will get answer of this question when you see next example, where we will be denoising images, right? And obviously we do not have noisy images, so we will also introduce noise into those images. So you will see that noise will be introduced in the image, and then we'll remove that noise also. So you will see that example, and then you'll get better idea of that. Okay, so I hope this example is clear. For the timing, we did nothing. We are just giving same image at the input, and expectation is same image will be at the output, right? So you can see our autoencoder is able to generate same image as it have seen in the input. So this diagram is clear, right? This model is clear. Now here's the next thing, the denoising autoencoder. They call it DAE, right? Now see here, if you just see it and you will understand, Nimra, this is 7, this is noisy 7, this is original 7, and this is noisy 7. And from this noisy 7, we have recovered original 7. So you can see, wow, what an achievement. This image has been converted to this image. You can see all noisy pixels have been removed. Only black and white pixels are here, and the intensity is properly maintained, that now again 7 is readable. This is original image. We will introduce noise in that, and from these noisy 2 we are recovering the actual 2. And the good thing is only noisy pixels have been turned to black, right? And those which matter, they are still there, they are still whitish. So we can read this is true. 1 noisy 1 recovered 1, 9 noisy 9 recovered 9, 0 noisy 0 and recovered 0. So we'll see this example. So all these first rows are showing the original images, this row, and this row, and these are the noisy images. We will see how to introduce noise in MNIST, because we do not have noisy MNIST, we have only MNIST. So we will deliberately introduce noise into images. And you know that in real world, when these images turn older, when they are 100 years old, they usually become like this. Lot of dots are there, lot of lines are there. So there is a way to introduce noise into image. Because we do not have noisy images available in our data set, so just for experimental reason, we actually introduce noise in our MNIST, and then we denoise our original images. हेलो
सर।
यस सर।
आपने सारा मेरा लेक्चर सुना या मेरा माइक ऑफ था?
सर माइक ऑन
सारा
था।
सुना है, अभी ऑफ हुआ, अभी ऑफ।
हाँ
सर अभी
सारा सुना है सर, अभी ऑफ हुआ।
ओके या मैं डर गया क्योंकि मेरे नाम के आगे ना ये लिखा हुआ था। एनीवे
सर
हाँ फोन से गला है।
Okay. Yes, sir. Yes, Irfan, go ahead.
Sir, but can we use this for image preservation? But I think we don't face this issue in digital format of image, do we? This the passage of time, the images get these noises.
You mean that this problem is already solved, eh?
I mean, in digital format, I think we don't get these noise in our images.
No, there is, even in digital images, there is noise. Noise is not only that when your image turns old, there are lines. Noise is maybe sun is in the wrong direction, a lot of lighting on your forehead, or maybe right. You have taken your image in dark, so you can convert those dark image into bright, right? So a lot of noise types are there. Even in digital images, if lighting condition is not very ideal, you can convert those into better images. And in some cases, wow, another application. I mean, low dimensional, images, you can convert them in high dimensional. So when you transport them in low dimension so that they can consume less bandwidth. But when they reach a destination, you can convert them in high dimension. So maybe a 16 by 16 by 3 image, which does not take a lot of memory, you can convert it into 2056 by 2056 by 3. So, upgrading its dimension, improving its quality is another application of these autoencoders. But
compression and decompression, right?
Yeah, you are right. You are right. But noise does not only mean in old images. Noise mean even the image of me that you are seeing at the moment. This one is noise. I mean, here you can see unnecessary light is there, so you can remove that light. And more importantly, probably lighting condition in my room is not very ideal. So if you want to improve my skin color, you can do it, right? Things like these we can do with autoencoders. Nimra, your question? Nimra, go ahead.
Sir, actually no question. मैंने hand sorry sir, sorry, mistakenly hand raise हुआ sir, sorry.
Okay.
So I have one question.
Yes, go ahead, please.
So I think that when it comes to the I mean the autoencoders, I think it's not used in real world applications. I mean, it's still improving. So this, I think that I have seen an article recently. There are modern approaches being employed in this area, like the, if I recall it correctly, VAE, variational autoencoders.
You're right. You're right.
So what is that? I mean,
you're right. You're right.
VAE.
Even GAN, generative adversarial network, they are an advancement in these autoencoders. They are also autoencoders because GANs are there to generate image, and autoencoders are also generating images. So you are right. A lot of advanced variants are there, but we will reach there certainly. But before reaching to VAE, we have to understand, what is autoencoder and what is its application in denoising. But the basic concept of DAE is same as the autoencoder because they are also autoencoders. Right.
Thank you.
Okay, so this beautiful concept of eliminating noise, let's implement it. So it should be denoising. So here again I'm doing same thing, loading the data set, doing this pre-processing, storing the image size, which is 28. Now we're going to introduce the noise. How to introduce the noise? With X train, I'm just adding another matrix whose shape is 28 by 28. So we are doing nothing. We just have a random matrix with normal distribution, right? With 0.5 mean and standard deviation, right? So we generate all these random pixels and add those random pixels in our original data. So you can imagine, just like this. Maybe if I am using Word, so say for example, maybe if I have maybe if say for example, this is my matrix, 1, 3, 5, 56. Say for example, if this is my say for example original image, right? I'm doing nothing. I'm just adding another random matrix in that. I'm just adding another random matrix in that. That's it. This is original image 1 plus 4. So obviously, when you add both of these matrices, each of your original image in the training becomes a new image, right? Becomes a new image. So we are doing nothing. We just we just add this noisy image into the original image, and that is the X train noisy, right? We do this for training, and we do this for test. So we will train them on training noisy images, and we test them on noisy test images, right? Now here, maybe after doing addition, your values might have been more than 1, which is not acceptable in our neural network. So we are clipping them. We say the range for all these should be from 0 to 1. So if the value is already in the range of 0 to 1, it will do nothing. But if the value is more than 1, it will clip it to 1. It means it will make it bright, completely white, right? So we clip both and training as well as test, right? Now, Nimra, I hope you got the answer. We had our training data, and from our training data, we have generated noisy images. And how to generate noisy images? Do nothing. Ultimately, this one is a matrix, 28 by 28 ka matrix hi hai na?
Yes, sir.
Same size matrix we are generating here. The size is equal to, the shape of the training. So same size matrix we are generating here, and that is nothing, just a random matrix. So that random matrix is being added into X-train. So obviously, if you want to introduce noise into the image, just disturb pixels. And how we are disturbing? By adding some random value in each of the pixels. So this X-train noisy are actually noisy images, and X-test noisy are also noisy images. Now we have got 4, set. 2 set are clear, X-train and X-test, they are clear images. X-train noisy and X-test noisy, they are their corresponding noisy images. So we have to do nothing. We just train our model that input is this, right, and output is this. So we say, when you see something like this, please generate this. When you see something like this, generate this. When you see something like this, generate this. So, we are doing nothing. We say at the input, during the training, at the input, we give this. We say generate these. So obviously, you are giving it 60,000 images. So the model will learn that these pixels, I need to turn them to black, and these pixels, I need to give them proper intensity so that they are displayable, so that they are white, right? So eventually, model will learn which of the pixel I need to convert them to black, and which of the pixel I need to leave with, white. So, this pattern your model will automatically learn when we do the training of deep neural network. It's nothing. Yes.
Sir, this is fine, completely fine, means we are generating noisy images. But sir, do we have any generalized model for that? I mean, for example, if I got some pictures which are noisy, I don't have data to train it, then how I will recover those photos?
There are many. I mean, there are models. There are some pre-trained models which are trained on noisy image, which is the noise in real world. The noise, because images have gone too old. I'm sure you must have seen your grandfather's picture. It will be very noisy, and the noise which is generally introduced, it is because people have kept that photo in their wallet, because they kept in wallet, so it has been folded maybe 1000 times. So a permanent line is there, and you want to remove that line. So there are pre-trained models. You just Google them. Those pre-trained models have actually been trained on such images. Those have been trained on such images. So if you give your grandfather's photo to that model, it should be able to produce the clean image of your father's photo, because this was a real world problem. They said, if you want to restore old books which are now completely damaged, you needed a model for that, and these models are already existing in literature. You just Google, you'll get those. They will tell you on how many images it has been trained and what are those images. Even if you Google them, you will get a lot of those century old images which will have the noise that we people want to remove, right?
Yes,
Okay. So we clip both of these. We are now clear that we have got 4 set: X train, X noisy train, X test, and X noisy test. Everything else is same. Everything else is same as in the previous case. Input shape is 28 by 28 by 1. You know, byte size is 32. You can change it based on your RAM. Filter size is 3. Latent dimension is 16. We mean that the intermediate representation of image will be 16. Filter is 32 and 64. Input, the way we did in previous example. So input shape is equal to 28, and I'm naming it encoder input. X equal to input, and then X equal to convo layer of 32, and then again second time X equal to convo layer of 64. So now after this loop, X is representing a CNN having input and then 2 layers of 32 and 64. We store the shape of X just for using it later on. We flatten X, right? And then we have this fully connected dense neural network. Obviously, the model developed so far, we are giving to this layer. Now latent is actually representing your whole encoder, right? So I create encoder equal to model, given input, apply input on this model and give it the name encoder. We display the summary. The summary of this model is actually this one. Same as you have seen in the previous denoising. Denoising. Its summary is same. Its summary is same as you have seen in the previous case. Right. Then latent input shape is equal to latent dimension, which we stored here. The latent dimension which we is stored here. Latent dimension which is latent dimension is 16. This one. So latent dimension. Okay. Yes. So latent input equal to this, and then X equal to, we first have dense neural network. We pass it to this vector which we have generated, reshape it to 28 by 28. No. Initially it is 7 by 7 by I think 64. So we add 2 layers of 64 and 32 in the reverse order as in the encoder, because this one is decoder. So we add 64 and then 32. Right. When this is done, we actually add this type of reconstruction, right, with the sigmoid as the activation function, and then decoder is equal to input, and we produce the output. Output is actually this whole model, right, and we name it decoder. Display the summary of this model, which is same. Finally, autoencoder is equal to inputs. We are providing input, and then supply those input to the encoder, and output of those encoded to the decoder, right? And then we compile the model, and now this is important. Wow. Autoencoder.fit. We say if these are the images, generate these images. If these are the images, generate these images. So we are giving them 60,000 noisy images and their corresponding clear images. So slowly, gradually, model will understand what I have to do with each of the pixels. It will make sense what are the noisy pixels and how I need to fix them. In this simple example, it knows that these are noisy pixels. In almost all the example, these are the noisy pixels. And what action it should perform? Just turn them to black. Just turn them to black. Right. So the thing is, the model will automatically learn, because we have got this beautiful gradient descent. We have got this loss function MSE. So initially MS will be very high. We are doing it for 10 epochs. So slowly, gradually, MSE will be approaching to 0. We are doing validation on the same test noisy. We do prediction. After doing prediction, we just 3 rows and 9 column. We just display few of those. The number of images, 27. So 27 images. It's actually this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. 9 and then 18 and 27. That is the reason why these are the dimension of the grid that we are going to display. So we are going to display 27 images and 3 rows and 9 columns, right? So we just concatenate them. So we say take images from test. These are original images. These are the noisy images, and these are the decoded images, which we have taken from our autoencoder, right? So X decoded for all these noisy images is stored here. We actually take those images from there, right? So we say 9 images from I mean 27, not 9, because number is equal to 9 into 3. So 27 original images, 27 noisy images, and 27 decoded images. We just then display them in the grid by using simple Python, and we save it the output in our in our folder on drive. So you can it is actually referring to example 2 these. So this whole grid, when I ran, I saw this one. So 7 noisy were recovered, 2 noisy decoded, 1 noisy decoded, 9 noisy decoded. So you can see this really is doing the job which we wanted this autoencoder to perform. Right. So with the simple technique, I mean, CNN is still same, huh? But this time it's not a classification, it is reconstruction of same image. Clear? Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Nimra, do you have any question? Nimra?
No, sir.
Okay. Abdullah, are you clear?
यस सर बट मैं सोच रहा था जब हम ट्रैकिंग कर रहे होंगे तो हम सेम चीज एम्प्लॉय करेंगे या फिर कोई डिफरेंट मेथोडोलॉजी होगी, जैसे हमने यहाँ पर जो है नॉइज इंट्रोड्यूस की तो फिर उसने डिटेक्ट किया कि कहाँ से मुझे नॉइज खत्म करनी है और फिर उस जगह उसने ब्लैक प्रिंट कर दिया ना, तो फिर इसमें एज डिटेक्शन या फिर ट्रैकिंग कैसे होगी?
Can you repeat your question? Actually missed a couple of packets.
जी सर, मैं कह रहा था कि मैं इसमें सोच रहा था, मैं इसको रिलेट करने की कोशिश कर रहा था कि जब हम एजेस डिटेक्ट करेंगे या ट्रैकिंग करेंगे तो वो कैसे होगी? क्या हम सिंपली ऐसे ही जैसे हमने इसमें नॉइज इंट्रोड्यूस की वैसे ही नॉइज इंट्रोड्यूस करेंगे या उसका कोई दूसरा वे होगा?
नहीं, the way would be we will give at the input will give images and the output will give the ages detected from those images, right? So your X train will have two things. Your X train will have image and the output will be the ages in that image. So maybe you provide 10,000 images and at the output you give ages from each of those images. Obviously you will employ some other maybe manual technique or maybe some canny age detection, but the thing is at the input you provide image and at the output you provide ages in that image, right? So with this combination it will understand how ages look like, how ages
right, sir.
And then when you provide the image and you test during the test phase, you do not provide ages, you say give me the ages. It should be able to do that. It should be
exactly
able to, right? So
sir.
obviously you need a lot of training data. For age detection you need two things, images and corresponding ages. So there you can say that if you see it from the classification point of view, you can say here the label are actually the ages. Label are actually the ages. So say for example, if you are passing this image, I mean this image of Besharal. So this is one age. This is one age. So you will provide this information of this age. This one is another age. So you will provide information of this age. Automatically your model will learn. You don't need to do feature engineering. You don't need to do the manual calculation. It will automatically, if you just provide input image and corresponding ages for maybe 10,000 images, it will automatically understand how age look like. And for the unseen images in future, it should be able to detect ages.
Okay, sir. Thank you.
Right. I'm very happy that you people are really thinking the different perspective that even I could not when I was learning it. Denoising, you have already seen it. I hope it is clear. The final application of these autoencoders that we'll cover today is actually, you know, denoising and then automatic colorization. Wow. Huh? If you've got grayscale, you want to apply color on that. You can see here, if this is the input, the things that your model has learned, it has learned that sky is blue. It has learned that, you know, the rice crop are green. Huh? It has learned that trees are green. It has learned that, you know, this mountain is bluish. Huh? So, you know, all these patterns it has learned because we have trained it. And again, the basic principle is same. You give, you know, grayscale images at the input and their corresponding color images at the output. Maybe provide 60,000-70,000 grayscale at the input and their corresponding you know, color images at the output. Your model will make sense of the coloring. Your model will learn these typical pattern, that sky is blue and, you know, trees are green, rice crop are green. So, you know, it will understand this pattern. Again, you know, encoder is same. You just need to provide a lot of data. Right. Let's do it on Cipher 10. We will convert Cipher 10 images in grayscale, and then see how images are colorized. Remember, in Python, if each of the pixel in RGB is multiplied by these values, they'll be converted to grayscale. This is a magic. I mean, see here, 0.299 plus red pixel plus 0.589 into green pixel plus this, the result will be a grayscale image. So we are drawing, we get an RGB image. Each of the pixel is being multiplied, and the sum is actually a grayscale image. So we pass here the grayscale, we pass here color image, and we return the dot product of that RGB with these three values. The result will be a grayscale image. Right. So you can see here, these are the test images which we have actually taken from the Cipher 10. You already know what is Cipher 10, right? So all these are the grayscale images, and these are their colorized version. The good thing is, again, you can see the color of horse. This really is horse, huh? And sky, water, huh? You know, lot of here again you can see sky. The color of sky is blue. The color of sky is blue. The color of sky is blue. Color of water is blue, dark blue. So you can see all these patterns the model has learned, because in Cipher 10 we have, I think, around 10,000 images. So on those 10,000 images, it has learned all these patterns, and then when we gave it grayscale images, it colorized them. Right, we'll see it. Let's see this example. Colorization. Yeah, this one is colorization. Right. So this time, I mean, this function I've already explained. This is to perform dot product between you know, all these values with 0.299, 0.587 and 0.114. Right. So we load Cipher 10, X10 and X test. Again, you can say I'm not loading label for the simple reason that this is not a classification task. So image, row and column and channel, you know, this is the first dimension, this is second dimension, and this is third dimension. In this case, obviously this is 3 because it is color image, so it is 3. Right. We'll be saving output on this directory. I take 25 images. Right. Initially, from X test, I take 25 images, and I I'm, I divide them in 5 by 5 grid, right? And display them. So the first thing which I'm going to do, I save this grid of 5 by 5 image. In each row I'm displaying 5 original taste images. So nothing, just produced autoencoder example 3. You can see the file name. The file name is tastecolor.png. So this tastecolor.png, tastecolor.png, taste color, this one. So you can see these will be my inputs. This one is lemon, this one is flower, there is a sky, there is a sky, there is snow. Let's see how colorization performs on this, how our autoencoder performs on this. So these are the 25 images on which we'll be operating, right? So these are our ground truth. We convert them in grayscale. You can see these are the grayscale version of those same images. And how we generate it with this, we say X train gray and X taste gray. All the images in X train and X taste, I passed this function, the one we have already written, which does nothing, which actually multiplies each of the pixel with this value, and this value. This actually magically converts these RGB images into grayscale, right? So in X train gray and X taste gray, we have got all those grayscale images. Same, I do nothing. I take first 25 images, display them in 5 by 5 grid, and save in tastegray.png in my save directory. And my save directory is obviously this one, right? So you can see these images are displayed here. Now the actual job, the actual work. So X train and X taste, I do pre-processing. X train gray and X taste gray, same pre-processing, right? I reshape them, shape 0, a number of rows, column and channel, right? All total images, total number of images. Reshape them gray as well. Then now I'm going to create encoder. So input shape is equal to image row and image column and 1, because it will be a grayscale image at the input. Byte size, filter size, latent dimension. Previously it was 16, but now it is 256. And here I'll be adding 3 layers. The first layer of 64, then 128, and then 256. Right. So my input is equal to same way as we explained previously. X equal to input. After this is kind of first layer in sequential model, right? So your input layer is here, and then I add 3 filter. The first filter of 64, 128, and 256, right? 64, 128, and 256. When this is done, I save the current shape, which is 4 by 4 by 256, right? I flatten it, and this actually gives me after dense layer, it gives me the latent image. Right. So I say my encoder is equal to a model which converts inputs to this latent value. Right. And I just display the summary of this model. Right. This is my encoder. Then here's my decoder. Again, my input is actually the shape of that latent dimension, which in this case is 256. Right. X equal to dense layer. Same way as we did in previous example. Then I add 3 filter in reverse direction. So 256 first, 256, then 128, and then 64 in reverse direction. I add these 3 layers, and then I do that transpose, right, to convert into the actual dimension. Decoder is equal to latent input and output dimension, which I have mentioned previously. Summary of this decoder. And I actually put encoder and decoder together as we have done in previous example. I name it autoencoder, and then we see the summary, right? And I do some intermediate step because this runs for quite a while. So I actually state some checkpoint. After maybe some time, I'm going to save the results. Again, last function is same, and then I fit. Input is grayscale, Autoencoder. Input is grayscale. For this image, this should be output. So I give around these 10,000 grayscale images and their corresponding color images. I validate on this, run it for 30 epochs with batch size 32, right? And then I do prediction. I pass these test images, I pass these test gray images and do the prediction, right? Because model has been trained. Autoencoder has seen that if this is the grayscale, its corresponding color will be this. If this is the grayscale, its corresponding color will be this one. So I have shown it. When you see this grayscale, here is its corresponding color. If you see this grayscale, here is its corresponding color. So you know, because it has seen repeatedly how color is applied when you give it a grayscale, it should not be changing the shape. It should be regenerating same image, but obviously applying those RGB values, right? Once if this is done, I just display, you know, first 16 images from there. I display those, right? So you can see here, if I deep learning for 2020 lectures, I think I have stored them here. So these are the colorized images. These are those colorized images. This is the output of the colorization. These are the original, you know, these are original. Come on. Why? This is photo. Yes. Right. So you can see these are colorized, predicted, and these are the ground truths. Yes, it is not very accurate, but you have to understand that it has not seen a lot of data, only 10,000 images. But you can see again, it has at least learned that water is blue. It has learned that sky is blue. Yeah, it may not be exactly blue, but it has still learned this. Wow, it has learned that, though, I mean, yeah, this is the water, but it has not learned properly. Yeah, but this color, the color of this thing, it has learned very properly. Yeah, at least you can see it has detected ages properly. Yeah, these are the trees which are green. These trees are also green here. Yes, a lot of mistakes are there. Here the water is blue, but here it has again applied the green color. It is not very accurate, but at least I mean some of the outputs are very correctly predicted. For example, these two animals, they were black. In the output, they are still black, right? Lemon is, you know, in this case it is yellow, but not yellow here, so it's a mistake by the model, right? Rose here is you know, yellow, but here it is white, so obviously it has not learned this pattern properly. It is only because, you know, we have not given it a lot of data. But the good thing is, come on, we predicted these images from, you know, these images. So that's a, you know, that's a good journey. You know, these are the predicted. It converted these gray to these color images. So yes, some colorization is happening. Sky is blue. Sky is blue. You know, water is blue. Water is somewhat blue. These animals are black. They are black. Right. So you can see it is not completely correct, but at least it has learned some pattern that how gray images are converted into color images. Certainly, if you provide it more data, it should be able to improve its performance. Right. Clear? I have displayed those same things here also. These are the ground truths. The horse, and when you see after training, yeah. Oh, I could not display it properly, maybe, but I have saved it in. I think this is after few epochs, but if you run complete epochs, the performance should improve. And not necessary on your machine you see same performance. It is only because I have displayed 4 images, so you know, kind of they have been splitted the pixels. But if you reduce the size, you should be able to observe it properly. Clear? Are you clear with the colorization autoencoder?
Yes, sir.
Yes, sir.
Does it excite you?
Yes, sir. Really, very excited.
Yeah, I mean, a lot of variations are there. VAE is another variation in these autoencoders. We'll see them in next class before we cover GAN. But the thing is, you know, this simple CNN, it can be used for these practical application of compressing image. Even in some cases, if you have got a low dimensional picture, if you want to increase its dimension, you can have a general purpose, you know, autoencoder for that. Maybe if you've got 60,000, maybe 100,000 low dimension images of 28 by 28, and if you have trained it to produce 1024 by 2048, you can do that. You can do that. So, you know, to increase dimension of the image, it can be an application. To do compression, it's another application. Colorization, another application. Denoising, another application. Segmentation, another application. You know, a lot of things we can do with the autoencoders. Yes, with the advent of GAN, autoencoder have taken the back seat, but still in a lot of practical applications we can use autoencoder and many of its variation. But one untapped area is obviously applying same concept on text. On text. I'm yet to see a use of autoencoder in text mining. I have not seen. I mean, this can be, if you can think over it, maybe we can come up with some idea where this model of autoencoder can be applied on sequences. In this case, it is being applied on image, but it can also be applied on sequences. And sequences means text or music or, you know, a lot of sequential applications can be there. Right. So any question up to this point? Okay.
No, sir, it's clear.
Okay.
No, sir. Shall we take sir namaz break now?
I think we can end here today.
Okay.
I thought it should take more than 3 hours, but we have completed in less than 2 hours. That's good. Eh? Anyway,
Yes.
so in next
You're
class,
good, Admin.
next class will be last class, and we will cover, you know, GAN in that class. Hopefully, that should be it. And how about your projects?
Sir, it's Rukesh. Kindly to extend the date for the projects. We are working. It's taking time.
What is the deadline of the project? What is current deadline?
15th January, sir.
Jan?
5th January, right?
Jan 15th
15th January.
Come on. Many days are still left. It should be only 5-6 days project, and you still have 15 days. So I don't see any need of extending the date. 15 Jan. Come on. Usually
Sir, make it on the
make it
Yes, it will be a round number then. 20s.
20th.
It would be good, sir.
20th. I haven't yet created the link, but if you see here, I mean, in the document I have mentioned the deadline, course project description, the deadline. Okay, this was the proposal submission. You people have already submitted the proposal.
yes, sir.
Yes, sir.
Okay, so I can extend it to 20. I will update it. I mean, next time when I create a link for your project submission, I will mention the deadline 20.
Thank you, sir.
Okay.
Thank you, sir.
Okay. Thank you. See you next week for the last class, and there we will also discuss about the final exam. I don't know when final exam is starting for master's program.
Sir, still we don't know.
Okay.
So
You have
Dr. GM will know.
okay. maybe we will receive it. We will receive it in the coming few days. Okay. Okay. Yeah, thank you very much. See you on coming Friday.
Thank you, sir.
Okay, sir.
Thank you,
Allah
sir.
Hafiz.
Thank you,
Allah
sir.
Hafiz, sir.
Allah Hafiz.
Allah Hafiz.